All right, so I'm back substituting for Julia today. She will be back on Thursday. I know you've got a test coming up next Thursday, so we're trying to piece together all of the parts and pieces and strategies of constant rate of change in order to figure out how to use those same techniques to measure accumulation when the rate is actually changing all the time. So I believe you saw this, a stagnant picture of this. Static picture? Static picture, that's what I'm looking for. Last week in a lecture, and then also over the weekend, you're asked to look at this and identify what all these mystery question marks might be representing. Maybe a little bit easier to tell when it's moving. So take a minute or so, see if you remember what all of the different question marks might have to do with our accumulation, which I know you went over the full sum last Thursday, but we're going to recap that again after going over all these parts, and then use this to do some computations, talk a little bit more about the left and floor functions that were introduced and why we need those, and then figure out how to make this a little bit more exact as opposed to approximate, which actually just involves some notational changes. So I'm not quite sure why this is jumping ahead a chunk at a time. I tried adjusting my end slider intervals, but that just made it slower. So we'll see. But in any case, taking a look at this, as it's moving, you can see along the bottom, there's this one black arrow that more or less continuously gets longer and longer. We've got this red question mark, single question mark that's jumping from spot to spot. And you can see the spots it's jumping to in advance on the independent axis. Other single question mark things, there's the blue and purple question marks, single question marks, on the independent axis. I'll call it x-axis here since we have x listed up above. And the purple question mark is always that same, it jumps from spot to spot, but it doesn't change sizes at all. And the blue, as you can see, and this is the part that was maybe harder to see from a static picture, the blue is this length between those red dots as it extends. So it's measuring a small changing quantity that just keeps restarting over and over. So there's one more single question mark, and that's a black one at the beginning that just stays put. So you can see we've got some changing quantities and some unchanging quantities. So we've got some variables and some other things. Now there's all the double question marks that are kind of labeling other things up above. But for the most part, let's see, are there any exceptions? Yes, there's one exception. The single question marks are all, except for one, labeling things that are either parameters or variables. There's one that's actually labeling a function. But this black question mark at the very beginning that isn't moving and is just right here, it's at some spot that seems to be maybe about a half on the x-axis or so. But relative to our accumulation and our sums, what do you think this first black question mark here is representing? Or what symbol is it that we've used before? Yeah, it's the initial x value for the accumulation. So when we're measuring accumulation, we have to start from someplace. It might be 0, it might not be. But if we're measuring net accumulation, which is actually what this sum is about, just using our rates, not having some starting initial value otherwise, just a net accumulation, we have to start from someplace, and we can measure onward to a specific other spot and have a numerical result, or we can talk about just in general measuring forward from there and describing that in terms of how far forward we go. But that first black question mark then, that would represent what was used in your sums as A. So let me scroll this up a little bit. I've got a whole bunch of little hidden parts in here. Ooh, there we go. You've played around with GC. Now you can do lots of weird things, but let's see if I can, where's my Q1? Here, I'm gonna make this a little bigger because this is not liking me doing two things at once. Let me just stop this. Maybe. There we go. We've seen it moving. My computer's not a very happy camper right now. So this first single question mark, that's that A. So we start someplace to measure accumulation. It's up to you if you're doing it on your own. If we're trying to do something together, somebody needs to pick it and declare it. Here's where we're going to start. So there's that A is where we start measuring our accumulation based on, well, some rate function. So this whole picture here, the idea is we've got an exact rate of change function, and we're trying to measure accumulation for that. So if this is supposed to be representing something that's helpful, this one function that's graphed up above where we have its continuous values shown there, that red double question mark curve, that's going to be our exact rate function that we're using. And its values keep going, but we only care about what its values are at starting from A, and we only use some of its values. Let's see, these are all in a weird order. 8. There we go. So that's our R sub f, our exact rate of change function, that red curve there. So back to these down here. So we've got A here, and this one I accidentally uncovered here, this other black single question mark. That's just our independent variable x, the one that starts from wherever and goes onward. Now we only care about using the values that are past A, but it has values all along. So in fact, it can go back past 0 here, but just we're only looking at first quadrant for simplicity's sake. So thinking about these other single question mark things here, what is this red single question mark that hops from dot to dot to dot? Any thought on what that might be? As x grew larger, yeah, this red question mark thing keeps hopping to the next red dot that's most immediately to the left of where x is. This left of x, it's a weird sort of function. The input to it, or the independent variable of it, is an x value, and the output is possibly another x value, most of the time another x value. The only time it comes out to be the input is exactly the same as the output is if the x value is at one of those red dots. But again, this left function is describing, given an x value, what's the left end of the interval that that x value is in. So these intervals are something that we define, and if you can see these red dots here mark off a series of intervals that are all the same distance apart. What do we call that distance apart that the x intervals are? What's the notation that we use to indicate the size of how big these intervals are? Yeah, delta x. Delta x is that fixed interval width. It's a parameter that we just decide on, just like A. Let's use an interval width of, looks like about 1.4 or something here. Let's use a random length interval just to make this confusing looking. But let me get back to these. So let's see. We've got, there's our delta x, the distance between those red dots. And let's see, I was also looking for a left of x. There we go. So if we're looking at this animation, you can see this delta x, each of those distances is a delta x. It's just labeling one particular one. But delta x is the distance between any two of these red dots. So just keep in mind, just for the purpose of this animation, this was hopping from spot to spot, but it's just showing what this distance is. We could have all of them labeled right now, but that would be a little bit too busy to look at. So we've got delta x, which is the distance between these red dots, or the lengths of our intervals that we're using. We've got this left of x, which gives us x values that are always at the beginning, the left side of an interval. And let's see, there's one remaining single question mark thing, which is changing in length, much like x changes in length. Only it seems to go from 0 to the length of an interval and then start over again. What's the notation for this small variable that varies within a delta x interval? It's kind of like x, but not quite. Yeah, dx. So we talk about dx is this variable that has x values that vary from essentially 0, not quite 0, to the width delta x. We let it vary, and then the whole purpose of doing this, splitting these up, is so that we can actually use our constant rate of change ideas. Here's my dx. There we go. So how this helps us use our constant rate of change, we know there's a couple of rules about constant rate of change. dy equals mdx. Change in the dependent variable is a constant multiple of the change in the independent variable, as long as we keep that one rate. So if I have a constant rate, that m, that constant multiple, then I take my independent variable times that, the change in my independent variable rather, times that to get the change in the dependent variable. Well, when I've got a rate function that's changing all the time, that's not very helpful. So what we do is, again, we take a few values from the exact rate of change function, and instead of using all of the infinitely many values that are infinitely close together, those dependent values of the red curve here, we just use some of them. Like for instance, in this, starting at a, we're going to use this rate, r sub f, at a for a little while, for one delta x worth of time, whatever that might be, or delta x worth of change. So how that helps is, if I, instead of changing rates all the time, if I use one rate for a little while, you can imagine, oh, maybe that's like if this is time on the independent axis, although I have it, long enough so you can see it, imagine that's a millisecond worth of time, and I use one rate for that long. All right, maybe not a big deal if it's really just a millisecond. Now my rate is actually changing, so after a millisecond, I'm going to go and pick a different rate to use that's more accurate and use that for the next millisecond, and so on and so on. Because if I have one constant rate that I can use for a little bit of time, that rate times time, or mdx, will tell me what happens to the, well, whatever quantity it is whose rate we were measuring. Maybe this is change in height of something over little tiny bits of time. So if the height was increasing by about, what does this look like, 0.55, somewhere between 0.5 and 0.6, 0.55 meters per second, and we use that constant rate for a millisecond, and then we change and look at this next rate of change of the height for the next millisecond, we can figure out how much the height changes altogether by accumulating each interval's worth of change in height and appending them together, adding them together. In this case, they're all positive amounts of change because we've got positive rates. So the remaining parts that we've got here is this black double question mark. This is representing these black lines that are going out there. And what that is, again, remember the red curve is representing a rate, an exact rate function, whose dependent values, the actual rates, are changing all the time. Well, the changing all the time is because it's going up and down. If I instead remain constant, a constant function goes horizontal, so a constant rate function, when I graph it, has the same rate all the time, which when I'm looking at a rate function, or a rate graph, a constant rate is like, y equals 3, y equals 5, horizontal line sorts of things. So let's see, where's my other, is that it? No. I know it's in here. Here we go, that's the last thing. My fake rate function, my approximate rate function that I can imagine using. I don't have to actually draw it, but if you want to see what's actually going on throughout all the x values, we're using just a few picked out values of this. Now, if I were to continue having x go on indefinitely far, then there'd be infinitely many of these little dots highlighted every delta x intervals also. But just looking at this is the rate function that we're actually using. Use this value for a while, and then the next value for a while, and the next value for a while, and so on. Picking one value at a time, because we can deal with that, mentally speaking, like, oh, m dx, we can do that. Pick one value of m, multiply it by the changes in x as they occur, and whether it's for a full, complete interval, like these 3, or whether we're in the middle of another interval, maybe it's not very far, the rate that we're using times however long we've used it for, whether it's a full delta x or some value dx that's still accumulating, Or if I'm done and say, okay, now how much accumulated? And I can say, well, I need to measure how long that dx was when I stopped and multiply that by this last rate, then I'd have a finished amount of accumulation. But in any case, all the pieces here, we've got an exact rate function and an approximate rate function that are graphed up above. There's not a graph of the accumulation that's happened, but from this, we can measure accumulation and could draw another graph of this or could create a function for it, up above, there we go, to describe what's needed. So the only thing is that this function, it doesn't have any of the details filled in. But this is what we worked on last time in class. So what I want to do is recap some of the pieces to this in general, starting at a general A and going on towards any general x in the future where we could substitute in a value for that later. So in other words, creating a function that says how much accumulates starting at A and going through any general x if I have a rate function, exact rate function, r sub f, or approximate rate function that I just call r. And we pick a delta x of general size for the purposes of writing this down. But for a computation, we need to have stated a specific value for a and a specific value for our parameter delta x if we wanted to do numerical computations. But just in general, we can use those parameters to placehold for later decisions to make. Any questions about the items in this before we go back to the sum from last time? All right, so I believe you did two versions of this, one with a specific value of x at the end, so a specific computation, and then in general, how do we find this capital A of x? That's an approximate accumulation. An exact accumulation, that's what we're working towards. We'll have a little subscript f, just like our rate function. The exact has the subscript and the approximate with just r. Our approximate accumulation is just capital A here. So if we want to start at x equals lowercase a and go toward any value of x, and in fact it can actually be less than a, it doesn't really matter. What we're working on is figuring out how do I figure out how much accumulated in all the full intervals, the ones that are delta x in width, and then add on the accumulation for the last little bit, if there is any, of a partial interval or a current interval. So for any complete interval, the idea was, well, we have all these spots, the left end of the intervals, but they're done. The left of x only gives one value at a time. For any x value, there's only one value of left of x. It's the left end of the current interval. Once you have a larger x, those previous values aren't still there. The left of x is just the closest left end of an interval to wherever your x is. So I can't refer to those previous things as left of x, but they used to be left of x when x is smaller. A, and then a plus 1 delta x width, a plus 2 delta x widths, and so on. And then the shortcut notation you talked about was using this summation to express that. This j minus 1, j was used as an index, and just the idea, again, for the first interval, we have the rate evaluated at the beginning, a. For the second interval, we need to go past one interval to get there. So I have, for the second interval's rate, I have a plus 1 delta x because I'm past one interval in order to be in the second interval. To be in the third interval using this third rate here, I have to go past two intervals, so a plus 2 delta x. So for a general jth interval, starting with 1 through whatever, so 1 would be the first interval, 2 would be the second interval. To be in the jth interval, I have to go past j minus 1 full delta x width interval. So a plus j minus 1 delta x puts me at the left end of the jth interval for any value of j that you want. So for the fifth interval, this would be a plus 4 delta x, because I've gone past 4 intervals and I'm ready to start the fifth. But again, this is the input to the rate function here, this a plus j minus 1 delta x. And notice this is the approximate rate function. I believe one of the questions you're asked to think about is, It was both in the textbook and in your homework assignment was, should I use the exact rate function or the approximate rate function? As long as the input is one of those ends of the intervals, either an expression like this or a left of x, it doesn't actually matter. Because remember, that's where those two functions are identical. At the left end of each interval, r of that value and r sub f of that value are the same thing. That's how you pick the r approximate values. So it doesn't actually matter. So I just have r here, but it could be r sub f as well. So there's a couple details left. We'll get to the where do we stop first. But for all the complete intervals, I have a rate that I use for delta x amount of time, for lack of a better general word to use. So I use it for delta x horizontally. Use one rate that I pick every so often. I pick it every delta x, I pick a new rate, and I use it for delta x with, unless my x value is in the middle of an interval. When I'm interested in finding a particular x value, I need to know how many complete intervals I have, and then what's the final interval, how long do I use that for? The final being this, as x is changing, the current interval. So my current interval gets to use the, instead of a plus something or another, I can use the shortcut left of x, because left of x means the left end of the current interval. So if I'm specifying that out, we're dealing with the current interval, I can use that instead. But if I know how many intervals it is, I can express left of x without using left of x. Left of x came from something. It's count up all the complete intervals, which we'll talk about that in a second, and then find the left end of the current interval. So this dx, what I'd like to have here, we're going to make one last change to this, aside from entering in the details of where do I stop my sum. I'd like this a of x to only have one variable. And remember that x and dx are both variables. I don't want to have two variables in this. Right now we have lots of symbols, but a is a parameter, r is a function, delta x is a parameter, that's a bunch of things added, r is a function, x is a variable, left is a function, but dx is a second variable. So we want to re-express dx in terms of x, but that's not too bad because dx is related to x, depending on wherever x is. I just need to know how far I am past the beginning of the current interval. And so that's just, oh, how far is it from x to left of x? That's how large dx would be at any point in time, which means I can just write it as a subtraction. I can write this as x minus left of x. Oh, sorry, this was doing the how many completed intervals question first. So to figure out how many completed intervals, I know you talked about this last time, but between a and x, if I want to know how many completed intervals, I need to know how big delta x is and divide, essentially. But I need a whole number, because I need to, how many completed intervals, I don't want to say 4.6 or something. I want to say a whole number. So we just figure out, you know, how far apart they are. If it goes from 2 to 17 in groups of 0.25, 17 minus 2 divided by 0.25, and then just make it a whole number, but round down. You don't want to round up and overestimate. So that's that floor function. So you figure out how far x is from a, how far the end is from the beginning. Divide it up into how many times does delta x fit inside that, to divide it up into little chunks, little intervals. But then this floor function just rounds down that result, because we don't want to end up with fractions or decimals. So this subtract and divide, round it down to the nearest, oh, not to the nearest, round it down to the next lower whole number. And by the way, if this does come out to be negative, because as I briefly mentioned last, let's see, 10 minutes ago, it doesn't actually matter if x is larger than a or smaller than a. You can actually do this backward. You can start from a and accumulate going back to the left and then like unaccumulate if you want to. This isn't, we generally look at it one direction for simplicity's sake, but if that happens to come out negative, you can throw an absolute value on it, make it positive. To count how many, I don't care about positive or negative. So if you do run across something where it comes out negative, just strictly following the formula, we just want to know how many intervals. We don't really care in what direction those intervals lie. But in any case, x minus a over delta x, and then round down to the next lower whole number, gives us a number of complete intervals. Beginning minus n, divide up into how many little chunks, how large a chunk you want it to be. So that gives us a way to express how many complete intervals. And then, as I said, the other fill in the blanks we already talked about, x minus left of x, gives us a way to express that dx quantity without using a second variable, without using both x and dx. Using a single variable, we can just use x as the independent variable. And this expression has a lot of parts to it, but x is the only thing that's a variable. Delta x and a are parameters. R and left are functions. J is an index. So get comfortable with all the pieces of this. You're going to have a take-home quiz, I believe due on Sunday. Julie's going to put in the due dates for this. I'm going to hand it to you today, but it'll be a take-home quiz that you'll upload into Canvas like last time. And it'll be about using some of the parts of this to express certain things, or how do I count this and that. Make sure you're comfortable with that. Your test next week will also have a significant portion of like identifying what the different pieces of this do, understanding what the symbols mean within it. So it's not just a, oh, this is just some mess that they're throwing at us and we're never going to have to use this because integrals. No, I want you to understand what all the parts of this are, what they're for and why what we're doing works, instead of just, and then we get to an end result and so we never need to know math again. But in any case, there's one other part of this that I wanted to mention, and I don't think my little writing thing is cooperating. Let me try. Yeah, it's being uncooperative here. But let me try. Hold on. It's being stubborn earlier. There we go. All right, so let me just open up something blank-ish. This is what we're going to look at in a second. I'm just going to use this for a writing area for a minute, so don't worry about this for just yet. But if I want to express left of x, remember left of x is a whole function that defines what's the x value at the left end of the current interval. So we can express left of x without writing left of x because I know how to count intervals. I know how to find out how many complete intervals there are for any x past a, just based on a and delta x. So I should be able to express this in a more roundabout way, which is not, it's like not that we'd like to use this because it's a nice shortcut. But there are other ways, just using, addition, subtraction, floor functions, those sorts of things that to define left of x, to define what we mean by left of x. So to figure out what left of x is, remember we want to know what's the x value at the left end of the current interval. So left ends of intervals are things like a plus delta x, a plus 2 delta x, and so on. So that's the x values at the left end of the current interval, or left end of various intervals. So if I want the last one, meaning, well, wherever x is, for any general x, how would I express the left end of this interval I'm currently in? I need to know how many complete intervals, and then go past all of those. So the how many complete intervals, that was the thing on top of the sum, if you remember. So on top of the sum, we had this, how many complete intervals? X minus a over delta x. That tells me how many complete intervals, as long as I round it down to a whole number. So if I want to go past all the complete intervals, just like a plus delta x is past one interval, a plus 2 delta x is past 2 full intervals to be the third interval. If I want to go past that many intervals, well, I'm going to be at a plus, this is some number of delta x's to go past this many delta x's. So this expression here, a plus x minus a over delta x floored times delta x, that can express left of x. Now, is that pleasant to look at? No. But that can express left of x without using this function left. If you want to use left of x in GC, left is not a built-in function in GC. You'd have to tell it what this is. The sine function is built in. There's lots of things that are built in. Logarithm functions are built in. Left is not one that's built in. If you wanted to use left of x in GC, you'd have to define left of x as this, where notice x is the only variable in there. You'd have to tell it what a and delta x for any particular situation that you'd want to use. Those parameters you have to define. But this expression here gives you an x value at the left end of the current interval because it starts at a and adds on a bunch of interval widths. How many? Well, whatever x minus a over delta x is. So we've gone past all of those. All right, so. Yes. The current x. Yeah, so wherever we've, like, if you can imagine x starting from, negative infinity or wherever, and just going forward, whatever the current x value is, figure out how far it is from a, where you cared about accumulating from, and find that distance. So x you can think of as like the end for any particular value of x. That'd be like the end of the accumulation that you're looking at. Yeah.
Could you just explain maybe briefly what the difference between this and the actual sum is?
Oh, so this right here is just an x value. And in fact, this is left of x. So left of x is the same as this expression here. Left of x gives us a much shorter way to write that. So left of x we care about when we're trying to find the accumulation in the current interval because we have to express where do I use those rates. So notice there's no rate involved in this expression here. So if I want to measure accumulation, I have to have the rate at the beginning of an interval. So the rate evaluated somewhere times how long I use it for. So some sort of x value. So I need a rate times something to get an accumulation. A rate or an m times some amount of change in x, whether it's a part of an interval or a full interval. It's kind of up, so depends on what you're doing. But in general, that net accumulation, we have a whole bunch of different rates times a delta x, and then plus a rate times that last bit. You might not have a full interval for any particular x. There might be a little part of an interval left over. Wherever your x is, you're going to have this rate times a dx, or this x minus the beginning of that last interval, x minus left of x. So you're going to have a sum of a whole bunch of mdx's. And that's the idea. The whole idea is that your sum is a whole bunch of mdx's, and that last term that isn't part of the sum from the current interval is just another rate times another dx. So it's all that mdx or y equals mdx. So you're having a whole bunch of changes in y. So this is not a very good way to write this, but just general, how does this relate to what you spent your time doing before your first test? You've got a whole bunch of different rates, each one times the same change in x. And so we have a whole bunch of rates times, and this dx was always that delta x that we chose. This one is not going to be that. If there's any extra left over, it's going to be somewhere between 0 and delta x. So this is something that's smaller than delta x if we've got this one, if we've got any stray left. Now you could a through something, and that something could be precisely the end of an interval, in which case you don't have to worry about any tag on a little extra weird part. But the idea is that this whole accumulation uses your methods of constant rate of change, rates times changes in the independent variable, over and over and over, just added together, because you have a bunch of different rates. Instead of having one constant rate that works for the whole time, you're using constant rates for little bits of time and then reevaluating and picking a different, better, approximating constant rate at the end of each small interval. So let me sum that up. I've got that on a different slide in a slightly more neat, maybe. Yep. Come on. There we go. So our approximate accumulation function, without all the details thrown in there, it's about our two constant rate of change principles that we talked about before. So dy equals mdx. Any change in your dependent variable, any amount of accumulation of something, whatever it might be, is based on having a constant rate of change times a bit of change in the independent variable, whatever that might be for the specific context. But each summand, each of the terms of the sum has a rate times a delta x. The delta x is the change in the independent variable for a full interval, for complete intervals. And this r of something, r of a plus some number of delta x's, whether it's 0 or more, that's going to be the rate that we use for that, each of those delta x intervals. And then there's this straight term here, r times the rate function times dx, x minus left of x if you want, or x minus, you could change into that x minus a over delta x floor, that sort of thing. But the current interval amount of change, so something for dx that's less than delta x. So within this sum, we see that in two different ways. One's in the sum where there's a whole bunch that are very similar, just different rates, but same delta x each time. The current interval term, the only reason that's separated out is because this dx is going to be something that's smaller than delta x, something between 0 and delta x. So the other part of your constant rate of change ideas, in addition to dy is mdx, there was the y final is y initial plus dy, or plus mdx if you want. So that's in there also. Now, it's not like circle one thing, but notice we have a sum. We're adding together a whole bunch of things here. So we're adding together, you can think of it this way. Here's all of the stuff that's already done. Here's where I'm starting from as x is changing. But you could have fewer terms and have this starting from nothing and add on the first term of the sum. Then add on the second term of the sum. And add on the third term of the sum. But every time you stop adding terms of the sum, we've got a starting completed value, this y initial. And then this last term, this is the one where there are actually variables that are in there. If you remember from this doesn't have all the details written into it, but in the sum portion of it, the only place that a variable shows up is up in the upper limit of the sum, that x minus a over delta x. The x there is a variable. The rest of the stuff inside the sum, there's j's and a's and delta x's, parameters and index values, but there's no variables within that sum. So that sum, for any value of x, that sum is fixed other than how many terms there are. How many terms to the sum changes as x changes, but the sum itself is kind of fixed, and so the only part of this that's changing continuously as x changes is this last part. It just keeps adding on a little bit at that tail end, and then all of a sudden, boom, there's a new term to the sum. And then we keep adding on a little bit from the current term, and then boom, there's a new term to the sum. If you keep expanding x or keep increasing x, we keep getting more and more terms to the sum, and then a new piece here with a different rate that accumulates slowly but continuously. So these are our two constant rate of change tools. If I want to measure how much accumulation happens or how much change in my dependent variable there is, I need a constant rate times an amount of change in my independent variable. If I want to measure a larger amount of accumulation, or how much do I have now that I'm done, what did I start with, and then what accumulated, add that on. Where did I start from? And then add on some new accumulation in that variable. So this is all very general, whether it's running at a constant rate and then how far did you go? Well, then run at a different constant rate, and how far did you go there? How far have you gone altogether? Add them. Or it could be lots of different things, including, well, if you saw that graph that I had up earlier, I was talking about sand being poured onto a scale. So let me pass out this to you. What this is a chance for us to kind of use some specific context and numbers. Use the techniques of the sum to understand what each of those parts do. When we're dealing with not just in general and abstract ideas, but with specific numbers. Now, we're going to do some visual estimation. And this isn't something that you need to turn in. This isn't your quiz. That'll get to you later. This is an activity that we're going to, I want to give you a little bit of time to work on this individually, but first let me explain it. I'll get you started. But if you want to move to being nearer to somebody so that you can kind of compare notes, please do. But what you're looking at here is a rate graph, an exact rate of change graph. Here's the rate at which sand is being unloaded onto a scale. Sorry, but does anyone else I apologize. So you can see, it doesn't say how much sand is on the scale to start with. We don't really care. We're going to talk about net accumulation. So just starting from, on here it says A equals 0. So starting from time 0, at which point the sand was being poured, unloaded onto a scale at a rate of, well, I see this low number here. If you can see these, there's what? These boxes seem to be 0.25 then vertically. So 0.25 would be the height of this y-intercept here. What does that mean in terms of this graph, that this is at 0, 0.25?
At 0 seconds, sand is being poured at a rate of 25 pounds per second, I guess.
Yeah, 0.25 hundred pounds per second. So notice the units on this. Hundreds of pounds per second. So these are rates between, well, this low value at the beginning is 0.25. It gets closer to 0 at the end. It seems to stop pouring eventually. But up to nearly 5, meaning nearly 500 pounds per second. But it varies all along. It's not maintaining a constant rate throughout. So what we're going to do is, don't jump straight to this graph. That's going to be a little bit hard. But follow the questions down below. The first one asks you to think about what the quantities measured on the axes would be for both this rate graph, which we kind of talked about a little bit, and if, what we're going to do in a little bit, if you draw this accumulation graph, what would need to be the units if we're not going to institute unit conversions as a part of this? So it would be the units for both the independent and the dependent axes on both of these, the units and the quantities, not just the units. And then there's some steps. Number 2 says highlight points on the exact rate of change curve every 0.3 seconds. So this is our delta x equals 0.3 that's mentioned at the top. So we're going to use a equals 0 and delta x equals 0.3 and go about starting at 0, saying, all right, put a dot every 0.3 seconds. So this down below, these aren't in quarters. These are 1.1, 0.2, 0.3, 0.4, 0.5. So 0.3, maybe about here, and so on. So do dots every 0.3 seconds. And then on this same graph, as you can see in the instructions, it says sketch an approximate rate function using the left-end approach. In other words, make a constant rate that lasts for 0.3 seconds using each of those values that you use at the left end of the interval for which you're using it. So turn this into an approximate rate graph, or draw an approximate rate graph on top of this by drawing those horizontal constant rates. And where it gets a little bit tricky, just try to, you don't have to do a bunch of computations, you don't need to grab a calculator, but just estimate what the net accumulation starting at 0 would look like, and an approximate accumulation graph using a constant rate for every 0.3 seconds. So take a little while. I'm going to wander around for a bit. If you have questions, let me know. So there's a lot of different steps that are mentioned on this, just to make sure we're kind of going the right direction with this. So a lot of you are doing computations and things like that at this point, so that's fine. Just want to make sure we have the notation down, because the earlier questions were about notation. So the first question down below this asks you to name the independent and dependent quantities for both sets of axes. So just the independent axes on both of these should be the same for your rate and accumulation, unless you're going to do some unit conversions as a part of your computations. Your independent axes are going to remain unchanged. It's x for both. In this case, this variable was. What is this? Actually, oh yeah, let's say delta x. What is x representing? Time in seconds. Yeah, since time 0, whenever time 0 might have been as time on the clock. But I'm just going to label quickly here, seconds. So the vertical axes, though, the dependent axes, are not representing the same thing. If I'm looking at a rate graph, it says right here, it's the rate of change of the weight as a function of time in seconds. So this is in hundreds of pounds per second. So this is my rate of change. Now it's kind of written right there, of my weight in hundreds of pounds per second. If I'm looking at the net accumulation graph, what would these numbers 1, 2, 3, 4, 5, 6, what would those be? What would be the units on those? Yeah, just hundreds of pounds, which would be then representing the weight in hundreds of pounds. Now, specifically relative to how we did this, was just starting at time 0. It's not necessarily the total weight of sand on the scale. There could have been 500 pounds of sand on the scale when we started at time 0, and then we added some. So this is the added weight, is what it'll be, in 100 pounds, since time 0. Since x equals 0, since that's when we started, a equals 0. So it's the added weight labeled in hundreds of pounds. All right, so we'll get to doing the graph in a little bit, but one of the first things it asked to do after that was to highlight the points on the curve, and I did one already, but that said, and label them with label it exactly using function notation, and then approximate the rate values. So for instance, this first point is 0, it looks like about 0.25, but how could I express this location exactly? Instead of calling it 0.25, how would I label it exactly? Maybe it's not exactly 0.25. I could call it 0, yeah, r sub f, or what was it? Is there a letter on there? W, yeah, r sub w of 0, the rate of change of the weight at 0. Now I do want to have that subscript because I'm going to be drawing the approximate rate function. We don't have the approximate r function yet. So I want to label this point with it. If I'm going to use exact notation, the function notation, rather than estimating a decimal, I'm going to use r sub w of 0, or for the second point, which is at 0.3, and seems to be a y value of maybe about 1. But in exact form, I can call it, since I picked the x value to be 0.3, I can call it r sub w of 0.3. Oops, missing a parenthesis there. So we could label each of the points in that same way, but that'd be just 0.3, 0.6, 0.9. Now it said to go up through, let's see, we want to highlight points on the curve every 0.3 seconds, starting from 0 until 1.8. So not all the way to the end do we have to go, but every 0.3 seconds, we would do this sort of thing, and if I can follow lines properly, we'd have points 1, 2, 3, at 1.2, at 1.2, at 1.5 for an x value, at 1.8 for an x value would be the last one that it said to do. So highlighting points starting at x equals 0, every 0.3 units, delta x equals 0.3, through 1.8, which means if I were to measure accumulation over each of these delta x intervals that we have rates at the beginning of, I would have accumulation from x equals 0 through x equals where? Using just these dots. Will the accumulation end at 1.8? Yes or no? No, we have a rate at 1.8, which we use after 1.8. It would go up through 2.1. So, in other words, if we're drawing the next step here, drawing in our approximate rate function, the R function, we'd be using this constant rate of about 0.25 for the next 0.3 seconds. So each of these we use for 0.3 seconds, including the last one, which means that although we only drew dots up through 1.8, we use this last rate at 1.8 up through 0.3 seconds later, 2.1 seconds. So if we use these 1, 2, 3, 4, 5, 6, 7 rates, we would have a way to estimate the accumulation for the first 2.1 seconds, which should make sense. 7 rates, each for 0.3 seconds, 2.1 seconds worth of accumulation. Now, in terms of drawing an estimate graph, kind of annoying, like without doing exact approximations, without doing the exact computations here, it's hard to get these values, but just thinking about, all right, this is about 0.25. I'm going to use it for 0.3 seconds, and that comes out to 0.075 of accumulation then if I do MDX. So this first MDX, I did have maybe about 0.25, that's my rate, times 0.3, which is 0.075. So this is 0.075 100 pounds, otherwise known as 7.5 pounds of sand went onto the scale during the first. But if I want to represent that here, I don't want to represent just this number. If I want to represent accumulation, I start from 0, it's net accumulation, and we increase from there because we've got positive rates. But for the first interval, I'm increasing really slowly. If I'm supposed to increase to a total of 0.075 100 pounds, and this first mark up here is 0.25, well, you can see this is going to be extremely low. So I'm just going to draw something right here because I can hardly draw a line that's any flatter than that with my ability to draw on this thing. So, meaning this dot here at the end is supposed to be at 0.3, comma, that's 0.3 seconds, 0.075. Now, does it look like it in that graph? Not particularly. It looks a bit higher than that, but 0.075 is really hard to graph. So, we'll just go with this. If I wanted to do accumulation during the later intervals, there are much higher rates of change. So I'd have a steeper graph, and I might be able to figure out where it goes from there. But just, let's see, during the next interval, this looks like a rate of about 1. So it looks like 0.3, comma 1. And if I use this rate of 1 for the next 0.3 seconds, it should increase by 0.3. That's increased by 0.3, not have a y value of 0.3 in this next graph. Because what I'd be doing is taking and adding onto here dx of 0.3, dy of, or dx of 0.3 and dy of 0.3 times 1, to make a total of 0.6, and then 0.3 more than that, 0.375. So this is this 0.075 from the first interval plus 0.3 from the second interval, a sum of 2 terms to have the accumulation from 2 intervals. So 0.375 is maybe about here. Oop, can I draw a straight line? No. So this would be straight line segments. Apologize for my messy, can't draw on this thing particularly well. But this first line segment should be relatively flat, and the next one a little bit steeper, because I've got a low rate, 0.075 pounds per, or what would we say, 0.25 pounds per second, and then 100 pounds per second, 0.25 100 pounds per second, and 100 pounds per second. and then the rates get higher and higher. So without doing computations, I'd have like, all right, I'm just going to freehand this, like, okay, higher rate, higher rate, higher rate, and then lower rate. It goes higher and higher, and so it kind of goes up and over like that. This graph doesn't go, the accumulation graph wouldn't go down. Why doesn't the accumulation graph on the right go down?
Even though the rates are decreasing, they're still over zero. They're still positive rates.
All right, exactly. These are all positive rates. There are large positive rates and smaller positive rates, but they're all positive rates, meaning accumulation should always be increasing, sometimes faster and sometimes slower, but always increasing amount of sand accumulated, increasing weight of sand accumulated, sometimes increasing slowly, sometimes increasing quickly, but there's at no point in time is sand coming off the scale. At no point in time are there negative rates. The rate is, or the amount is not ever like negative 0.3 pounds per second or something. It's always positive. So this graph would always be increasing faster and slower. Getting the exact points is kind of tedious, but these are just estimate points anyway, so I don't want to spend time on trying to get more precise approximations when they're only approximations to start with. So let's take a look at the last question on this front page. I'm going to clear this off and scoot down. The last question on this front page says, you know how fast a quantity is changing at every moment, and you want to know how much of it you have at every moment. So this consists of a process of 4 functions. We've dealt with 3 of them so far, and we're going to talk about the 4th one in just a little bit. Last thing for today. So far in the worksheet, you followed the progression through the first 3 functions. Write the names and descriptions of those. Let's see, what did we start with? What was given to us in the graph on the left? It was a rate function, yeah? And then we drew a different rate function. So the difference between those, the one that they gave us was an exact rate of change function. And then we worked towards getting an approximate, I'm going to abbreviate here, exact rate of change function. We had that nice curved thing that described how the sand was being poured onto the scale. The weight was increasing at varying rates from low positive numbers to high positive numbers and then back to low positive numbers again. But that gave us an exact rate of change function. We used a few rates off of that, 7, as I recall, 7 different rates instead of infinitely many, as our approximate rate of change function. Notation-wise, we had R sub W of X, and R of X is what we use for approximate rate function. It's just a piecewise constant when we graph it, the rate function. So the thing that we were messily sketching and is kind of difficult to do, involves lots of computations if you want to be more precise about it, but we can kind of get a general idea of what it looks like. That was measuring accumulation, but only using our approximate rates instead of using all of the rates from the exact rate function. So it's just an approximate accumulation function. Which we call capital A of X. Now, there's one other word that I want to throw in here. We have these rate of change functions. When we measure accumulation, you can talk about how much altogether of something there is from all time, or you can talk about just what accumulates during a certain interval, which would be our net accumulation. We started at time 0 and went forward from there, not caring whether there was anything on the scale to start with or not. So what we have was just a net accumulation function. I'm going to throw that word in here. So this is from 0 to X, as opposed to caring about what happened before 0, just the accumulation that happened starting at 0 and going onward. And we've got one more step to follow, and it doesn't have to do with the net here, but what we'd like to do is get an exact accumulation function, whether net or total, and the only difference between a net accumulation and a total accumulation is, did we start with something already? If we did, then we can just pop one extra number in there, plus whatever we started with. It's like y initial plus whatever happens afterward. But to get from an approximate accumulation to a more exact accumulation, and to a better and better and better approximate accumulation, but we want it to be exact, we're going to have to do something other than just using rates every 0.3 seconds, because we're ignoring all the stuff that happens in between. So our goal is to get to an exact accumulation function, and it'll be net still, unless we add on a starting value, which that's not a big deal. And we'll call that A sub, same thing as the beginning, A sub W of X, the exact net accumulation of weight. And this is, again, from, in this particular instance, from time 0 to time X, how much accumulated. If we want to do that, if we want to get exact net accumulation instead of just approximate net accumulation from time 0, we need to use smaller intervals. And in fact, I want to imagine shrinking the intervals so far that I can't even, see the distance from one end to the other. If I can do that, I can make it as exact as I want. I can make the intervals as small as I want to get the precision that I need to make more exact and more exact results in this accumulation. And eventually, there won't be any different, like if I can keep shrinking the intervals, those delta x's, eventually I won't be able to see any changes, visually speaking. And if I need more accuracy for some reason, like I'm working on, I don't know, something more important than just sand on a scale. Maybe I'm working on making sure people don't fly off the surface of Mars when we're trying to land there. Maybe we'll, zoom in, shrink down farther until it's as close as we want. We can do that. We can make delta x as small as we want, but we just get to, instead of trying to count all those bazillions of intervals that we end up with then, we just write a different notation for this. So I'm going to skip over the back side of this right now, but do take a look at this as a part of what I'm going to ask you to do between now and Thursday. Take a look at the back of this. It's going through the computations of how do I find all the y values in that accumulation, what do I get, and how do I end up with the final amount of accumulation by time 2.1. Using this 0.3 seconds at a time. It's a lot of number crunching stuff, but it's a practice at using the notation of the summation that we use to get accumulation in order to do this. So take a look at that. But what I want to talk about before we're out of time today, just quickly, is the notation for this exact net accumulation. So get this out of the way. That is not what I wanted to look at. Yeah, this will do. All right, so you've seen these sentences before. In fact, one of them was at the bottom of the front side of the worksheet. The two fundamental things that we do with calculus is either you know how much of something you have at any point, at every point in time, and want to know at what rate it's changing, or the reverse, which we were just working on. You know how fast a quantity is changing at all the time, any moment, and you want to know how much you have at every moment. So those are reverse issues from one another. Starting from a rate, figure out how much I have, or starting from how much I have and looking at that, how do I describe the rate? So the first one's called differential calculus, and in a lot of calculus courses that's addressed first, but we're doing the second one first. This is called integral calculus. And the notation that we use to express exact net accumulation is called an integral. So integral, like integrating and differentiating. Integrating is putting together all of the pieces. So like integrating, put things together. We're combining all of the pieces of information from all of the separate intervals to get one total out of this. So from an exact rate of change function to an exact accumulation function, we'd like to get something that looks like this instead of our jagged, every so often we change angles slightly. So we use approximate rates of change to visualize how can I come up with anything at all. But past that, I can imagine, well, add up all the changes to get accumulation, and if I want a better estimate, make smaller intervals. So if I make this delta x very small, instead of looking at pieces that are big enough so that I can draw them, it does get hard to draw. It gets hard to count also. Well, you just end up with, like, all right, how many complete intervals do I have? 2.6 billion, no big deal. I'm definitely not doing that by hand. Computing it is annoying. But this is one of those functions that GC does have built into it. The integral function is the function that takes us directly from an exact rate of change to an exact net accumulation. This integral function does. And what it does is all of those steps kind of built into one. Like, well, it doesn't have left built in, but as integral, as it turns out, integral is a little bit easier for it to understand, so it's also more frequently used. This is the notation for an integral. If I want to find the exact net accumulation, a sub f of x, this is just, it doesn't, there's not a magic like, oh, now I know how to get this. This is just representing, this expression is representative of, I have an exact rate of change function, r sub f, and I'll talk about the t in a minute, but r sub f, and then I want to, this symbol here is the equivalent, this is a Germanic s as opposed to your Greek s, sigma, but this Germanic s is also standing for sum. I'm summing up all the rates times d something. Now, why is it t instead of x? Hang on a second, but we're going to add up all of the mdx's from a to x. Now, what this t is here, t is a different, just like when we did the sum, we had that j that showed up. It's just that index that lets you know things. T isn't quite that, but it's kind of the same idea. I let t take on not just like values 1, 2, 3, 4, 5, so that I come up with the left ends of intervals. I let t take on all of the values between a and x. And so t is a different variable. Sometimes it's referred to as a dummy variable, but it's not meaningless. I let t take on all the variables between a and x, and I evaluate what is r sub f of t times dt, or let t vary from a through x, and do all the mdx's, all the rate times a little change in the independent variable, and add them up. So this s-looking thing, that's called our integral sign, means to add, just the same way that the sigma symbol does. This doesn't tell you how to do this, but this expresses what has to get done. So this notation here means, instead of doing an approximate accumulation where we use parts every so often, and we have to deal with all the details of how often, and what about this incomplete interval and a complete interval and all this, we don't have to worry about that. This symbol expresses, this notation here expresses the exact accumulation due to rate function r sub f, where we measure accumulation starting at a and going through any general x, or you could also include a number up there also, from a through 17. And then I measure all the rates between a, whatever a is, and 17, add them all up. This doesn't, again, this doesn't tell us how to do it, because there'd be infinitely many of them. But this notation expresses getting that. And that's what we're working at for right now. How do I express exactly measuring accumulation due to an exact rate function that changes all the time? I use all of its values between a starting point that's defined as a parameter and a general ending point, or an ending point as a number, either one. All right, well, you'll talk about more details of writing expressions like this correctly next time, as well as a few other details to wrap up. But as you know, like, so next time, a little bit more on integrals. Tuesday next week will be kind of wrap up, prepare for your test, and then Thursday next week is your test number 2, just before spring break. All right, so that's it for today. Thank you very much. Julia will be back on Thursday, and I'll have assignments posted for you a little bit later. Take-home quiz.